Welcome back to NE 630 nuclear reactor analysis or nuclear reactor physics. So today will be the last lecture in the reactor kinetics work. So we solved the point kinetic equation. We graphically solved the point kinetic equation for the three situation where you have supercritical, critical, and subcritical reactors. And then we moved on and we deduced the one delayed neutron group equation and also studied the three cases. And we noticed that the asymptotic period is the period that the reactor will grow up with or decay with. In case of decay with, it will be the longest decay time of the delayed neutron precursors, and this will be 1 over lambda 1 as we just stated clearly before. So we will conclude with how to calculate or determine the neutron kinetic parameters, stuff like the reactor period, for example. So let's start. So experimental determination of neutron kinetic parameters. So let's assume that we have inside our nuclear reactor, you knew that we measure the power inside the nuclear reactor using a fission chamber or ionization chamber or whatever technique you have, and then you calibrate this to give you the power, yes? But let's assume that we have R of T is the detector response for neutrons. Of course, R of T will be just some constant. Let's call the constant something like, we'll make it something like, I don't know, some functional form multiplied by n of t. And this functional form here will have a geometrical factor, and it will have some calibration constant on it. So whenever you have n of t, you multiply it by this calibration factor, you will get the R of t. We knew from the neutron kinetic equation that n of t goes like e to the power of what? T over tau. And this is t here is what we mean by asymptotic period. So this is usually, if you look at whether you solve the seventh solution or not, whether you solve the seventh solution or not, it will be just, this is the S1. And of course, if your rho is 0, you do not have any period, the reactor is stable, and S1 is 0. In case of negative reactivity, no matter what you will do, you will decay with the longest decay time for the precursors, which is governed by 1 over lambda 1. So we are talking about the case where we have a positive reactivity insertion, and this is the asymptotic period here. So again, if you multiply both sides of this equation by the function here, you will have R of t equal to R naught e to the power of t over tau. So our goal is experimentally to calculate the reactor period here. So all what you will do here is just take the derivative of this with respect to time. This will give you a constant, and this will give you 1 over t, and it will give you t over r, and this is again is nothing more than what? R of t over tau or t, and if you bring 1 over r dr of t by dt, which is ln r of t is equal to 1 over the period. So if you want to get the period, you can take the reading from the reactor panel. Yes?
This is e to the power of t over r or
T over T, sorry. Thank you. So all what you will do is just get the values from the reactor control panel, look at the power, and then try to see when is the power will what? Will double or whatever. Or this will be the doubling time, but you want to get the reactor period, for example. So just look for this ln of r of t and plot it with respect to time, and it will give you 1 over t. So according to our reactivity formula, the Einhauer formula, reactivity was given by S, and S is the root of the Einhauer equation here, and it is the inverse of this one. So I can write it as 1 over t multiplied by gamma plus the summation of I equal 1 to 6 of beta I divided by S plus lambda I. Again, S is nothing more than 1 over t. And you knew that n of t is just given by after you decay, the 6 other roots will decay, and you will end up with the asymptotic formula. This will give you a naught e to the power of s naught t, and again this will be a naught e to the power of t over t capital. So s naught is just 1 over t, 1 over t capital. So let's study the case where you have a supercritical condition. So if you use this formula and you divide by beta, so this will give you rho over beta is equal to gamma over beta multiplied by t plus the summation of beta I divided by beta multiplied by 1 plus lambda I t, and this is nearly equal to beta I divided by beta divided by 1 plus lambda I t, if you neglect this term here with respect to this term, because this is 10 to the power of minus 5 and this is 10 to the power of minus 2, 10 to the power of minus 2 or 3, and the reactor period is, let's say, in seconds. So you'll have something like 10 to the power of minus 2, this term, and this term will be 1 plus something, and this ratio is nearly 1. So okay, guys, so we can use this method several methods to calculate the asymptotic period. the first method, we'll call it the rod drop method. And what's the rod drop method is, we will have a critical position at, let's say, t equal to 0, rho is equal to 0, our reactor is critical, and you have your control rods are held at, let's say, this is your core, and the position for your control rods like this. And the other control rod bank was here. So at t equal to 0, this was the control rod position. You have rho naught, for example, the reactivity at the very early beginning, we'll call it 0. And then after, let's say, before 0, it was like this. Then at 0, I drop the control rod. So my reactivity versus time will be something like this. Then you drop it to certain reactivity from rho naught equal to 0 to rho 1, for example. So you drop it to, you drop it here, for example. So your control rod will come dropped up to here. So the initial detector response is R naught is proportional to N naught, and this is just before rod drop. Then after rod drop, it will be R1, which is proportional to N1. Now, we knew from last lecture that we have something called the prompt jump approximation. Can somebody remind me what we meant by prompt jump approximation? Yes, so the prompt jump approximation is, we, because of the short time scale of the jump or drop or the response of the prompt neutrons, and this time scale is what? The neutron lifetime, gamma. So we said that we will assume that the prompt neutrons will react instantaneously. And because of this, we reach to a relation, and this relation was what? N1 divided by N naught is just equal to the reactivity beta minus rho naught divided by beta minus rho 1. And again, N1 over N2 is proportional to R1 over R2, so this is just R1 over R naught, and rho naught is just 0. So from here, you can just deduce that R naught over R1 equal to 1 minus rho 1 over beta. So this is the detector response just before the drop of the rod, and this is the detector response just after the drop of the rod, for example. And we knew that rho over beta is equal to what over there? The formula over there. I equal 1 to what? To 6 beta I divided by beta over 1 plus lambda I multiplied by T. So if you knew what's the neutron response, neutron detector response before and after the rod drop, you can get what? The reactor period. So this is called rod drop method. The other method is called source jerk method. Source jerk method. And this source jerk method, unlike the method for rod drop, you need to have your reactor supercritical so that you will do the rod drop. You need to start critical, then you increase the reactivity to certain rho value, and you drop the rod after a while. But this one, you will do it with a subcritical system. And this system is maintained critical using external source. And all of us at the very early beginning, we stated clearly that you might maintain your reactor critical if you have what? If the reactor is subcritical, you can maintain it at a critical position if you have extraneous source inside your core. Yes? So we will have a subcritical rho less than 0. We will have an extraneous source inside the core, so our reactor is what? Will be held critical, and then the source is S, and we have N naught and C naught are just the neutron and delayed neutron precursor concentration at the criticality using the extraneous source. So if you write the neutron kinetic equation, this is just dN by dt rho minus beta divided by gamma multiplied by N naught plus the summation from I equal 1 to 6 lambda I Ci naught. This is just while you are critical, and this will be equal to 0. Why 0? Because you are critical, so you do not have any time rate of change of n. Yes? I am critical with the source. This is why I added a source term here. So if the source now is jerked, so the prompt jump approximation immediately after the source has been jerked is just rho minus beta divided by gamma N1 plus the summation of I equal 1 to 6 lambda I Ci naught equal to 0, and this is prompt jump approximation after source is jerked. So somebody will ask why I have this. First of all, last lecture we showed that the prompt jump approximation is, you will assume that there is no time rate of change of the neutron population for the prompt parts. So we equate the equation by 0, and we assume one of the things in the prompt jump approximation is just right after the change, after the source has been jerked or after the control rod has been removed from the reactor, that the delayed neutron precursor concentration does not change. Yes, so it has inertia. You cannot, just by removing the source or by by removing the control rod. You cannot just change your delayed neutron precursor concentration to a new value just after removing the control rod. Yes, it will take time because this depends on the formation in the fission, then the decay, beta decay, and instantaneously the decay by neutron, delayed neutrons. So this is why I put lambda I, Ci naught, and Ci naught, it was just the concentration just before the jerk. Okay, guys? So we can use this equation, and we knew that the equilibrium concentration, if you study the radioactive decay, and you knew that the equation for dC by dt is equal to what? Beta I divided by what? Gamma I multiplied by what? Ci of t minus lambda I Ci of t. Yes? This is the equation. How to get the equilibrium position? What does mean equilibrium? If you have a production and a decay. So you either will have something like this, or you either will have something like this, or you will have something like this. Yes, for Ci of t with respect to t, it depends on how fast or slow the decay and your production with respect to the decay. Yes, so if you do not decay, so this will be what? This will be this case. You are increasing C naught or Ci of t increases without any limit. If your decay is very short, very rapidly compared to the production, so you will be in this situation. So you'll grow up to a maximum, then you will decay very fast. But if your decay is shorter than your production, you will reach to an equilibrium state. So what does mean equilibrium here? That dCi by dt equal to what? 0. So this will be equal to 0, and you will have beta I and beta I over gamma I minus lambda I this is n. This is n. So Ci will be what? But now, this is n of t, and at equilibrium, I do not expect that this will be just after you jerked your source. This is the value for C naught. So it is beta I n naught divided by gamma lambda I. So you can use this equation, and you can use the Brombault jump approximation, okay? And also use rho over beta equal to 1 minus R naught over R1 to be able to calculate the parameters like T, the period, for example, or if you want to calculate any other parameter from here. So now we will start a fresh topic, and this fresh topic will be just the feedback mechanisms, temperature feedback coefficients, and reactor dynamics. So this topic will be temperature feedback coefficient. reactivity. So our reactivity will change with temperature, and the temperature rate of change of reactivity is denoted as alpha t, and alpha t is just the temperature feedback coefficient. Okay, guys? So what's the definition of rho? Rho is equal to what? K minus 1 over K. Where K is the effective multiplication factor, and we remove effective from the formula here. So alpha t will be just d by dt for K minus 1 over K. So for if you do this will be 1 over K square dk by dt, but usually K is a small value above 1, so you never get something like 1.2 or 1.3 or 1, the effective, not the infinite multiplication factor. So usually K is 1.00 something, 1.02, 1.0 something. So K square will be roughly what? But it will be roughly K. Yes, it will be roughly K. So we can approximate this and said that this is 1 over K dk by what? By dt. One over K dk by dt. Can I rewrite it in a more mathematical or an elegant form? What's 1 over x dx by dt? Yeah, so I can write this as d by dt of ln K. Before moving on and getting the criticality equations and so on, just I want you to get some feeling of the Brombaut critical situation and so on. You remember what's the Brombaut critical situation? 1 minus beta multiplied by K is equal to what? Equal to 1. How did we get this one? We got it from rho is equal to what? Beta, and what's rho? K minus 1 over what? K. So beta is equal to what? 1 minus 1 over K. Then 1 minus beta will be equal to 1 over K, and this will give you 1 minus beta multiplied by K is equal to 1. This is just the derivation of this one. When you have a reactivity equal to what? Equal to beta. So this is why we said that this is the Brombaut critical situation. So we'll give you beta for some isotopes. Uranium-235 uranium-233, plutonium-239. This one is 0.0065. This one is 0.0022, and this one is 0.0026. Which one is more favorable for you guys of those three types of fuel? Why? Less likely to be prompt critical. Yes? So if you made a mistake and you take off your control rods, you introduce beta, you most probably will hit the lower value of beta, lower value of rho, and highly unlikely you will hit the higher value of rho. So if you work with a plutonium or uranium-233, if you just by mistake reach it to 22.0022 or 26, you are prompt critical. While this is not a prompt critical in case of uranium-235. You need to reach up to 0.0065. So it is very hard to control the fast reactors compared to the thermal reactors, and this is the reason why. Okay, guys? The reason why is because of this beta value here. Okay, one of the reasons why it's very hard to control the reactor is you do not have a big margin to play with. Okay, guys? So now, let's return back to our business. What's K? Effective. It's K infinity multiplied by the non-leakage probability, and this is just eta epsilon F resonance escape P and L. But if I have alpha T, it's just equal to d rho by dt, which is just equal to 1 over K dk by dt. So this is just 1 over eta epsilon P F B N L multiplied by d by dt for eta epsilon F P P N L. If you do this, you will here do what? Differentiation by part. So differentiation by part, when you do the differentiation by part, it will be the differentiation of the first multiplied by the second, and the second multiplied by the first, and so on. So if you do this, you will end up with alpha t is just equal to 1 over eta d eta by dt plus 1 over epsilon d epsilon by dt plus 1 over f df by dt plus 1 over p dp by dt plus 1 over pnl dp nl by t. So you just transformed your coefficient, temperature reactivity coefficient, to sub-coefficients. And this is, we can call it what? Alpha what? Alpha eta. And this one we call it what? Alpha epsilon. This one we call it alpha f. This one we call it alpha p. And this one alpha p and L. So this is the eta temperature coefficient, reactivity temperature coefficient. And this is epsilon reactivity temperature coefficient. And this is thermal utilization reactivity temperature coefficient, and so on. Now, let's look for a phenomena that we already discussed before, which is Doppler effect. And again, we studied this several times. We knew that sigma gamma is just sigma naught multiplied by energy E naught over E gamma gamma over gamma psi and you knew that psi, the function psi, is just given by this formula. And x and this is the resonance integral. And we also discussed the flux self-shielding inside the energy of the resonance. And if you just want you to remember it, it was like this is the energy A and this is the resonance, and your flux will be just depressed inside the resonance. And if you remember, we give the following formula: P for the resonance escape probability, P equal to what? Negative N fill multiplied by the resonance integral divided by C sigma P, or potential scattering. If you remember, this is the formula for P. So if we want to evaluate alpha T P, so instead of this, you can write it as the same acronym like the book, like alpha T, the superscript will be the parameter, just everything subscript will be temperature and superscript will be the parameter that you have. So if you have the alpha P by the T is equal to what? 1 over P dP by dt. Where do you think we will have the temperature hidden here in this formula? So let's look at it. NF is the fuel number density. C is the average energy loss per collision, and sigma P is what? The potential scattering cross section, which is just constant 4 pi r square. Yes. So the only thing that we will have the temperature effect is this resonance what? Integral, because it has what? Sigma gamma, and this is sigma gamma here, and the function psi is the function that has what? temperature because it is in what? It is in here, in this. Okay? So we will end up with 1 over P multiplied by TP by the TF. I can make it like what? It will be if you do this substitution for P and dP by dt, it will give you ln P multiplied by 1 over I di by dt. For uranium oxide fuel, UO2 238 and thorium 232 O2. The resonance integral at 300 degree Kelvin is just given by 11.6 plus 22.8, some function called SF divided by MF, and this is just the fuel surface area, and this is just the fuel mass. So I at any T, temperature TF is equal to I at 300 degree multiplied by 1 plus beta double prime of square root of Tk minus square root of 300. So for uranium oxide, this beta double prime is just 61 10 to the power of minus 4 plus 47 10 to the power of minus 4 SF divided by MF, and alpha T P will be just negative ln 1 over P at 300 Kelvin multiplied by beta double prime 2 over the square root of TF in Kelvin. So that's just a handy formula to tell you what's the temperature. So if you want to include the fuel and moderator expansion because of the temperature, here we just looked at what? The Doppler effect, and we stated that NF is what? Does not change with time. But what if you have a thermal expansion? So in this case, if you want to look at the fuel and moderator thermal expansion on P, so the formula will be 1 over P dP by dNF, the change of the resonance escape probability with respect to NF multiplied by dNF by dt. And this will give you ln P multiplied by 1 over NF dNF by dt. And this will give you negative 3 theta F ln P, where -3 theta is 1 over T dN by T, and this is equal to 3 over rho d rho by dt. Rho here is not the reactivity. This is the thermal expansion coefficient. So B will increase, rho will increase, or theta is the thermal linear material linear expansion coefficient. So rho is still the reactivity. So what happened is, when the resonance escape probability will increase, rho also will increase. So I will stop here and I will continue the moderator effect next time, and also continue on for the same business. Did you get the idea behind this? Idea is just you want to look for what's the coefficient, temperature coefficient. Whether it's the activity temperature coefficient, you can divide it to several temperature coefficients. Eta temperature coefficient, epsilon, F, P, and P and L. And then you will look for what's the functional form of temperature of each one of those, how it changes with temperature. For the resonance escape probability, as a first look, we said, okay, let's look for what changes with temperature. And we said, it's the resonance cross-section in the Doppler effect. Then we said, okay, what if we have thermal expansion for the fuel and the moderator? So we have to also do the differentiation with respect to what? NF with respect to what? With temperature. And you have to find what's the relation between NF and temperature. Of course, this is all of you took in the 101 physics, which is the thermal expansion of the material. The material, the temperature increase, there is a volumetric change, whether it is volumetric thermal expansion coefficient or linear thermal expansion coefficient, if you are talking about certain direction, not in a volume direction. Okay, guys? So this is just the business that we will be doing for the next maybe 1 or 2 lectures. Then we will finalize this chapter, and we will start the new chapter about the fuel depletion, the isotopic build-up inventory in the reactor, the poison due to samarium and xenon, and we will conclude the course by 2 or 3 lectures about different types of nuclear reactors. Have a good day.